On the night of January 31st, 1953, the North Sea rose faster than the Netherlands could react. Wind and tide converged, pushing water inland along a coastline never designed for it. Sea walls and dikes did not fail because they were weak. They failed because the system assumed the sea would arrive alone, not as a combined force. As breaches opened, water rushed inland with nowhere to go. Rivers could not drain, land could not release pressure, and the coastline turned into a trap. This was not a failure of height or strength. It was a failure of assumptions about how water behaves under extreme conditions. More than 1,800 lives were lost, not because defenses were absent, but because they were static in a dynamic system. That night forced a different question. Not how to build higher walls, but how to redesign an entire coastline system. The Dutch coastline was never a single line facing the sea. It was a network of inlets, rivers, tides, and sediment moving at different speeds. Salt water pushed inland from the North Sea, while fresh water pressed outward from rivers. Pressure built where these forces collided. Closing one opening altered the balance everywhere else. Water diverted, currents accelerated, and stress migrated across the coastline. Engineers learned that every intervention triggered a chain reaction. The coastline responded as a connected system, not isolated structures. Designing defenses now required predicting how water would move hours and days ahead. Managing time became as important as controlling space. The coastline had to be understood as a dynamic system, not something to block permanently, but something to manage over time. Higher walls appeared to be the logical solution after 1953. Raising dikes promised safety, but it also amplified the forces they were meant to resist. As walls grew taller, water pressure increased behind them. The sea did not disappear. It stored energy against a rigid barrier. When static barriers fail, they fail completely. There is no gradual release, only sudden collapse under accumulated stress. Rigid defenses also trap water on land. Rain and river discharge had fewer paths to escape once the sea was sealed off. Each added meter of height reduced flexibility within the system. The defenses gained strength, but steadily lost the ability to adapt to changing conditions. Engineers realized walls alone could not solve a dynamic problem. The sea demanded a response that could change with conditions. After 1953, engineers stopped asking how to hold the sea back. They began asking when water should be blocked and when it had to pass through. This shift turned time into a design variable. A barrier no longer had to stand forever, only at the right moment. Water volume and flow speed became controllable factors. Instead of resisting force, engineers planned how much force the system would accept. Infrastructure began to behave like machinery within a larger system. Instead of fixed walls, it was designed as components with defined operating modes. A defense system now needed states of operation: open during normal conditions, closed only during extreme events. This question reshaped everything that followed. The coastline would no longer be frozen in place, but engineered to respond. The core idea of the Delta Works was movement. Barriers were no longer permanent walls, but structures designed to change position as conditions changed. Under normal conditions, these barriers remained open. Tides flowed, ships passed, and ecosystems continued to function. When storms approached, the system changed state. Gates closed only when water levels and pressure crossed predefined thresholds. This selective closure reduced pressure on the coastline. Instead of absorbing constant force, structures engaged only during critical moments. By opening most of the time, the system avoided trapping sediment and fresh water. Long-term ecological damage was minimized by design. Movable barriers transformed coastal defense into active management. The coastline was no longer sealed, but continuously regulated in response to conditions. The Delta Works was never meant to react in panic. Its most critical decisions were designed to happen before the storm arrived. Water levels, wind direction, and atmospheric pressure were monitored together. No single measurement was trusted on its own. Engineers defined thresholds long before emergencies occurred. These limits determined when barriers would close and when they would remain open. Once those thresholds were crossed, the system did not debate. Movable barriers shifted state according to rules already set. This removed hesitation from moments of crisis. Human judgment shaped the rules, but machines executed them consistently. The strength of the Deltaworks was not steel alone. It was the logic that decided precisely when steel should act and when it should remain still. The Deltaworks was designed around a simple rule: water must always have a path. Stopping it completely would only move the problem elsewhere. Rivers still had to discharge into the sea. During normal conditions, barriers stayed open to prevent pressure from building inland. Rainfall added another layer of risk. If inland water was trapped too long, flooding would come from the land instead of the sea. The system balanced pressure from two opposing directions at once. Sea surges pressed inward, while rivers and rainfall pushed outward against the same space. Managing this balance required timing, not brute force. Barriers closed only long enough to break the surge, then reopened to release water. The Deltaworks did not try to defeat water. It managed flow, pressure, and time as parts of a single, coordinated system designed to stay in balance. Protecting an entire coastline meant no single structure could carry the risk alone. The Deltaworks was designed as a distributed system, not a single point of defense. Instead of relying on one massive barrier, engineers divided the coastline into sections. Each segment was designed to handle only a portion of the total load. If one component failed or required maintenance, others remained operational. The system was built to degrade gradually, not collapse at once. Redundancy was intentional, not excess built into the design. Backup capacity was treated as a core requirement, not an afterthought. This approach allowed the system to absorb uncertainty. Storm intensity, timing errors, and partial failures could be tolerated without total loss of control. Scale did not make the Deltaworks fragile. It made failure local, contained, and manageable across the system, instead of catastrophic at once. The Deltaworks was never designed for a single storm scenario. It was built to operate under conditions that engineers could not fully predict. Sea levels change slowly, but relentlessly. Storm patterns shift, and rare events become more frequent over decades. Engineers accepted that no structure could guarantee permanent safety. The goal shifted from certainty to risk reduction. This meant designing for thresholds that might one day be exceeded. The system had to buy time, not promise absolutes. Maintenance, monitoring, and revision became permanent tasks. The coastline was no longer finished, but continuously managed. Living with uncertainty became part of the design philosophy. The system was built to adapt, not to declare victory. By building the Deltaworks, the Netherlands accepted permanent dependency. Safety now depended not on land, but on continuous system performance. This dependency changed risk itself. Failure became less frequent, but far more consequential when it eventually occurred. The Deltaworks is often described as a wall against the sea. In reality, it behaves more like a machine that never truly shuts down. Its components open, close, wait, and respond. Time, pressure, and probability are treated as variables, not threats. This approach cannot guarantee absolute safety. It only reduces risk to a level that society is willing to manage over time. As sea levels rise, even adaptive systems face limits. Every engineered solution exists within boundaries set by physics. The Deltaworks does not promise victory over nature. It offers time, control, and choices where none existed before. In the Netherlands, the coastline is no longer just defended. It is continuously negotiated by a system designed to think ahead.